For this example, we're asked to graph a sequence. We graphed a sequence in the last section on arithmetic sequences, and I don't know if you recall, it seems a bit strange that we're just seeing a series of numbers here. How do you graph that? Again, you have to remember the first value of the sequence has an associated variable n, which that's your first term. This has an associated variable 2, n is 2, this has n is 3, etc. So these make points, where this is considered to be our input, this is considered to be our output, so that first term of 5 is really associated with the point 1, 5. This would be 2, 15, this is going to be 3, 45, and that's going to be 4, 135. And that's what we end up plotting. Now, when we set up our graph for this one, you should notice that the values of n are all positive, so we're only going to need the positive component of a horizontal axis. Again, all of these y values are positive, so we're going to need the positive part of the y-axis or the vertical axis. So when we set this up, it makes sense to use just the first quadrant graph, like this. Remember, this isn't really the x-axis, it's really the n-axis, but if you call it x, I'm not going to mark it wrong. This, you could call it the y, but it's really the sequence, which geometric sequences, I typically call them g sub n. It's fine to use a sub n. Now to set this up, I'm not going to be using the same scaling. I just have to count up to 4, 1, 2, 3, 4. And I have to work my way up to 135. What I'm going to do is look to see how do they change from one to the next, and I see that I'm multiplying by 3. So since I'm multiplying by 3, to make my scaling easier, I'm going to split that largest value. I'm going to set it right here to be 135, and I'm going to split that distance into thirds. So right there, that looks like it's split into thirds roughly. And if you think about it, you should be able to figure what this one is, because this times 3 should be that. So this is your 45. And if you realize that's now 45, if you go up another 45, that'll make this be 90. And look, if you go 45 past 90, you're right up to 135. So that's the scaling we have. You could have done it another way. I think that's the easiest way to approach it. And now the points, we're going to plot 1, 5. This 15, I realize, is 1/3 of 45. The 5 is 1/3 of 15, so that's going to be very low, the 1, 5. The 2, 15 is going to be up 15, 2, 15. And the 345, I'm just going up to that amount. And the 135, sorry, is up right here. Now, the thing that I want you to take away from this is, if you would imagine connecting these, I hope you remember that we did do graphs like this. They were called exponential growth curves. So geometric sequences, so they grow through multiplication. They're going to grow very rapidly. That's again the phrase, something growing exponentially. If we have a sequence that has a constant ratio that is a value between 0 and 1, it's going to be an exponential decay curve. We're going to see it go down very rapidly and taper off towards that horizontal asymptote.